And the talk title is Minimizing Resources of Quantum Devices with Control Theory.
Thank you very much, Ahmed. Thank you very much, Dvira, and all the other organizers for inviting me. I'm awake since 2:30 this morning, so I hope I stay coherent, but if not, please bear with me. Okay, so I think as we heard yesterday and earlier in this conference, this is a quite exciting time, and it has been already for a couple of years, because I think what we're experiencing is the dawn of quantum engineering. And quantum engineering means that finally several fields of academic thought and activity are coming together, namely physics, electrical engineering, math, and computer science. And they all need to interact coherently in order to create non-trivial quantum states. And what for me personally is especially exciting about this is that it is control that turns scientific knowledge into technology. So control is really a common denominator in this endeavor, no matter what exactly your background is. Now, there's one problem with control, and that is that it means many things to many people. But I'm using it here in a quite specific meaning. So let me define that. And it's sort of the mathematical control theory setting where you consider dynamical systems, and you want to steer the dynamical system from some initial state or some set of initial states to some final states using external controls. And that's a framework that is quite broad and general and also has been very successful. For example, you can steer spacecrafts and make sure that you land the spacecraft on the moon or some other outer space object without crashing it. And you can reduce this example even to a homework problem if you consider the spacecraft to be a point particle, like in physics we like to do. And then solve Newton's equations of motion together with the control problem, and this is solvable analytically. Now here we're interested not in classical dynamics, but in quantum, and I just put up one example, it's really pretty random, of a conditional gate, of a conditional evolution of two spins. So here, when I say control theory or quantum control, I mean we want to use external fields to steer the dynamics of quantum systems. Okay, and then the control problem can be formalized in this way, that given the equations of motion and the target that you have to specify, and we still have to think about this, find the external controls that lead you from the given initial to the desired final states. And typically the controls enter our Hamiltonian as electric or magnetic fields and so on. Okay, so this is one way of seeing it, but before you set out to actually solving this inverse problem, you may want to pause for a moment and wonder whether your problem is actually solvable. Okay, so this is the other side to control theory, and that is there is a whole set of tools which are summarized under the title of controllability analysis that allow you to answer this first question. And then when you're ready to set about solving the inverse problem, there also exists a whole set of tools, quite mature and now also adapted to the requirements of quantum information for the second part. And I'll just mention them very briefly and will not go into much detail on this later on. So in particular, there's optimal control theory that comes in two variants. So there is one which is based on variational calculus or the Pontryagin maximum principle, and that leads to gradient-based optimization methods. There exists a whole set of tools. My own preferred one goes back to the Russian mathematician Koch, and we've contributed a Python implementation of this method, which is particularly general. That's why I like it. And you can find it on GitHub together with a quite extensive documentation and examples. And the other option is parameter optimization. So here you do gradient-free optimization. And also for this, there exist many, many tools that are ready to use. So we really have the tools to use. And maybe I'll move this a little bit up. So to answer these two questions, namely, which targets are actually attainable and how to choose the external controls. As I said, for question number one, the tools are summarized under controllability analysis. And let me give you one example. And that is, there exists a property, evolution operator controllability, that you can test for with a yes or no answer. And if the answer is yes, it means that any U in a given Hilbert space dimension can be implemented. And this is, of course, a prerequisite for universal quantum computing. Now, what I will tell you later on is that we can use this set of tools and turn it upside down and ask, usually, I mean, you answer this question given the Hamiltonian. So given the couplings, given the external controls. But now we can ask, let's reduce the couplings and controls and see if we can still retain controllability. And in this way, minimize the resources that we need for universal control, quantum computing. And in the second part of the talk, I will focus on the second set of questions, namely how to choose external controls and then look for pulse shapes for specific tasks like state preparation or gates for quantum computing. And you could also do sensing and really pretty much every task that you can think about. And you can use these tools to answer questions like what is the shortest possible time in which you can implement these operations. You can include additional constraints, use them to try to avoid decoherence, and so on. Okay, so this is the outline of the talk. So let's first focus on controllability and asking this question. And why this is relevant, I think, is very visible from this picture, where you see in one of these superconducting qubit architectures, the control lines for the external controls that are needed for state preparation, readout, and gate execution that go into these fridges. And just in terms of physical space, you cannot, I mean, grow these indefinitely. So that's one of the motivations. So what means controllability, or when do we get it? I told you it's a yes or no answer. And it's based on the so-called Lie rank condition, which is a sufficient condition for a system to be controllable. And why this gives you the right answer can be understood in a very nice, intuitive geometrical picture. And that is, given the system Hamiltonian, you can partition it in the part that has no external controls. We call it the drift in control theory. And then operators which couple. So these could be electric dipole moments, magnetic dipole moments, and so on. Okay, and then for this Hamiltonian, you construct the dynamical Lie algebra by taking nested commutators of the terms in your Hamiltonian. And what are these commutators? Well, they tell you in which direction your evolution can move, right? Because you can think of the Hamiltonian being in the tangent space of your unitary evolution, which you can think of as a generalized Bloch sphere. And then if your the basis of the Lie algebra here is full rank, it means you can move in any arbitrary direction and therefore reach any point on the Bloch sphere. Okay, so that's why testing for this condition will tell you yes or no, this can be done. Now, if you think of having to do this on a classical computer, then obviously this is limited to a small number of qubits because we have the exponential scaling of Hilbert space. So I'll tell you now two contributions that in my group we have recently done to sort of alleviate at least partially this problem. And one is still on classical computers, to not construct the Lie algebra explicitly, but instead to do it using tools from graph theory. So we map the Hamiltonian onto a graph where we treat the drift So the eigenstates of the drift Hamiltonian as nodes and then the control as edges. And we can do this because there exists a theorem in controllability theory that if you have a connected subgraph where all the vertices all the vertices are connected, but the edges are decoupled, so you're not exciting, let's say, this and this in the same way, then your system is controllable. And the advantage of doing this on the graph is that then you can actually evaluate the commutators also on the graph. You don't need to look at the huge matrices that are your operators. Okay, so here's one example just to illustrate the philosophy. We took a 5-qubit system inspired by the IBM Keto setup at the time. And if you looked at their specifications, you had X controls on each of the qubits, which are shown here, and then couplings of XX plus YY between all the nearest neighbors. Okay, so obviously this system is completely controllable, but you don't need that many controls. You can reduce the number of controls to just 2 on those inner qubits, so to speak. So you just have 2 controls of X type with the same couplings, and you still have the ability to carry out universal quantum computing. If you're willing to consider also different types of interactions, you can actually reduce the number of external controls to a single one, namely on this qubit here. And then you need also a ZZ type of coupling. So that, I think, was a little bit surprising. And it really, I think, suggests to think about how to choose, how to design your architectures to optimize the resources that you have. So the number of controls can be reduced to 1. Of course, there's a price to pay. There's no free lunch. And that is the gate operation time, of course, increases. So eventually, you may not want to go down to the limit of a single control, but balance the number of controls and the execution speed. Now, with graph test, controllability is still hampered by the exponential scaling of Hilbert space, because you need to be able to know the vertices in the graph. So you need to be able to know the eigenstates of your drift Hamiltonian. So if that becomes too large, then you can do what people always do when they are bothered by exponential scaling, and that is go to hybrid quantum classical algorithms. So use a quantum system to execute quantum evolution, and then a classical optimization on top to execute the algorithm. So here we are considering a parameterized quantum circuit, and where you treat the parameters of these operations on your qubits as a mapping from this parameter space onto the Hilbert space. What then happens is that this can be considered a manifold, and one can determine, thanks to an algorithm that was suggested recently by these people here, the local dimension of this manifold, which is referred to as dimensional expressivity, which in other words gives you the number of non-redundant parameters that you have to use in this circuit. And what we have shown is that there is a quite straightforward mapping between controllability and dimensional expressivity. And the nice thing about this algorithm to determine the dimensional expressivity is that you only need to add 1 auxiliary qubit in order to run the algorithm. So it's comparatively inexpensive. So how do we use this for controllability? Well, let's assume we have 3 qubits with controls. So we then define a layer consisting of these 2 steps, where we have 1 rotation that represents the action of the drift Hamiltonian, and local rotations that represent the action of the controls. And now we run this dimensional expressivity algorithm, and if we get dimensional expressivity of 2n minus 1, it means we have pure state controllability. In other words, from any state, we can go to any other state, but not necessarily simultaneously from several of those initial states to a set of other states. So again, let me illustrate this, how this works with an example. So here we have a 4-qubit system with XX couplings, and let's assume these are the controls. And you can, in this case, still figure out the algebra yourself, and you end up with dimensional expressivity of 29, which is smaller than 31. So it's not controllable, and that's also what the algorithm returns if you run it with different initial states and random arrays of these parameters. Now, you can reduce the number of controls, but place them in a smarter way, namely here in the middle. And in this case, the dimensional expressivity becomes 31. And in this case, we do have controllability, pure state controllability, and we find it with a minimum number of layers when running the algorithm. And now this is not yet operator controllability, where you get really arbitrary unitary evolutions, but you can use now the standard tools from quantum information, such as the Georgia-Markovsky isomorphism, to map this onto a larger system. So you need twice as many qubits as you want to test for, and then get also the yes or no answer on evolution operator controllability. Okay, so this is our contribution to the question number 1. How can we use these ideas from controllability analysis to optimize design of quantum devices? Let me move to the second part of my talk, where we construct actual pulse sequences to do certain operations. And my first example is one that from a theoretical perspective is very simple, is just going from one state to one other state, but it was the first time that somebody took pulses that we calculated in our group and used them in the experiment as is, so I really like this example. And the task here was to prepare so-called circular Rydberg states. If you haven't seen them before, this is the orbit of a circular electron, and you see why it's called circular. You see the tiny dot in the middle, that's the nucleus, it's to scale. And these states are characterized by a large value of n, that's why they're Rydberg, and then the maximum number of this projection quantum number, or in other words, it's the 2 states which are out here in this sketch of the energy level structure. The point about these states is that they have super long lifetimes, so they are very attractive for quantum sensing and quantum computing. And actually, for quantum computing, they have for a long time not been really seriously considered because they are so well protected, they're also difficult to prepare. But I think this has changed also because of the work that I'm going to show you. Okay, so this is a collaboration, as I said, with an experimental group at Collège de France in Paris. And the experiment was led by Sébastien Glaise. And of course, they already prepared these circular Rydberg states before we got into the business. These circular states were what Arroche used in the experiments that got him the Nobel Prize. But they could do this with a fidelity of around 80% using a generalized pi pulse. Now, in order to push this really closer to 100, you need to do this more precisely or faster. And this is a typical problem for optimal control. And here's the result that we got from our optimization. So these are the 2 quadratures of the RF field. And in our calculations, we stopped at 99%. In the experiment, they stopped at 97%. And the remaining error is mainly due to detection, the detection error, not necessarily the state preparation error. We also understand how this pulse works. Because this is one of the things that my experimental collaborators were very worried about. How robust is this? It turned out to be super robust. And the reason is that we're starting from this initial state. So this is the eigenstate of this Hamiltonian with low projection quantum number value, m equals 2. And we have to go to the circular state, which is the spin coherent state on the north pole of the generalized Bloch sphere. And what happens, what this pulse does, and you've seen here the funny shape of having these modulations first and then constant amplitude, is that in the first 40 or so nanoseconds, we prepare a spin coherent state. And then for the remaining time, we just rotate the spin coherent state up the Bloch sphere. Okay, and actually what came out of our calculations was not something quite as simple as this, but once we realized what happens, we could just get rid of those oscillations by hand and flatten them out. Now, my experimental colleagues were quite pleased that it really worked the way we predicted in the experiment, and then they asked me, can we also do something where we do not know a protocol for state preparation? Okay, and so we tried a superposition of the circular state and the m=1 state with a predefined phase, and it worked just as well with the same accuracy, again mainly limited by detection. And also in this case, the pulse shape is pretty simple and we understand the details of the dynamics. So I think this was a nice result because it convinces experimentalists that these optimal control pulses, even if they are not immediately obvious how they achieve the dynamics, how they do their job, they work. From a theoretical perspective, a single state-to-state transition is not very challenging. So here's a more challenging target. We optimized not just a gate, but a whole universal set of gates, and not just for one given system, but we considered transmons, fixed frequency transmons, which were coupled to a cavity which is driven, and asked how should we choose the system parameters in order to get the fastest possible universal set of gates. So what we found when we used a tool where we can optimize for an arbitrary perfect entangler, and when you start with gate durations which are pretty large, like let's say 200 nanoseconds here, and this plot are over the system parameters. So here you have the detunings of the qubits over their anharmonicity and the detunings from the cavity over the coupling strength. You see that this polyhedron in the so-called Weil chamber, I'm skipping the details, is almost full, which means we can implement almost all of the perfect entanglers. When we reduce this time, then fewer gates are left. And if we reduce even further to the limit where we can get an entangling operation, what is left is the square root of I swap. Which means we can use these tools from optimal control to have the optimization tell us what is the native gate of this architecture. And we find that we want to operate in the region marked by this dot here. So we are, what is light here are resonances. So we want to stay away from the resonances because then we're entangling too much and it will be hard to implement the local operations. But we also don't want to be in the dispersive regime where all the previous experiments had been, because then you're super slow. Okay, and then we can optimize for, once we have determined these parameters where we want to operate, then we can optimize an actual gate set, and here's the result. So we find quite fast operations for quasi-dispersive transmons. But transmons are anharmonic oscillators, so one may be worried a little bit by this anharmonicity, which in classical correspondence is nonlinearity. Okay, so here's the gates that we optimized, and what you see here in gray is the population at intermediate times during the gate outside of the logical subspace. So after the gate is over, everything is returned to the logical basis, so no worries about it. But if the nonlinearity kicks in, it will do so the more for higher excitations, and we do excite at intermediate times. So how can we quantify this? So here's another sketch of our system, the two qubits coupled to a joint cavity. We can use the tools from quantum chaos, and in particular, evaluate the Kullback-Leibler divergence to compare the distribution of the eigenphases of the evolution from the predictions of the Poissonian or Gaussian ensemble. And we've done this for all the sets in our gates, and you see in a few examples where you have here these blue showing up, we do have significant deviation from the Poissonian statistics, suggesting that chaotic instabilities may actually be there. We can analyze this further. So what is shown here, these are the eigenphases of our dynamics with the blow up of the first 5 nanoseconds. And you see there are a lot of avoided crossings in these. And here's the fit at specific time intervals to the Poissonian and Gaussian statistical predictions. And you see here and here, you're pretty Poissonian, but here there are clear deviations from the Poissonian or integrable case. Now, what turned out to be the most sensitive method to see these deviations is not the eigenfaces themselves, but rather their curvatures, their derivatives, because then we can distinguish which of the states are really affected from the overall average over the Hilbert space. And we find for several intervals, indeed, that we have this power of 4 in our distribution that would correspond to the chaotic statistics. Why would I worry? Why should this be relevant? Well, if you have these signatures of chaotic fluctuations, then it turns out that the gates are actually more sensitive to parameter fluctuations. So this is what we're looking at here, deviations in the detunings, in the coupling strength, or in the field amplitude or dipole moment. And you see that even though when we're close to the parameters we think we have good gate errors as soon as we move away, that's pretty unstable, which is not surprising. So at this point, let me switch gears a final time and look at more robust ways to control quantum systems. And that is via so-called driven dissipative evolutions, also known as quantum reservoir engineering. So in quantum reservoir engineering, let's assume we have dynamics described by a master equation. It's not a crucial assumption, but because what we're looking for in the end is the steady state of the evolution, and which means that this derivative has to vanish. And then the idea of quantum reservoir engineering is that we combine coherent drives in the Hamiltonian and dissipative evolution to create a non-trivial steady state. And you know examples from cooling, for example. So cooling is a simple version of quantum reservoir engineering, but you can also use this for more interesting states like entangled states or topological states. And an early example was looked at or done at the NIST group, where they used this idea and combined in the end 4 different coherent drives to entangle the 2 red ions, which are beryllium ions, and the 2 green ions in the middle are magnesium ions that were used for sympathetic cooling. And they needed a microwave, a sideband, laser cooling on magnesium, and key here is the so-called repump, which induces the dissipative step by going to a very short-lived electronically excited state. And this experiment worked. You see the results from some time ago here. But if you look at the scale, they were stopping at something like 75%. And first I thought, well, maybe, I mean, they're good experimentalists, but maybe still they didn't choose their parameters really optimally. So we optimized the Rabi frequencies, the polarizations, and we found you can actually push, if you choose better polarizations, you can push this from 75 to about 90%. But that's the hard limit. You can't go beyond that. And the reason is, and here we visualize the time evolution in the state space, the green blob is the target state, and you see that one of the microwave drives actually excites out of the target state. So the steady state of this evolution is not equal to your target state. So this was a nice control problem. And in this case, we didn't just optimize the parameters of the external fields. We asked which couplings are the best in order to make sure that we have the right steady state. And the result of the optimization is to keep the repump and the blue sideband, to choose a different microwave transition, obviously, because this was causing the problem, and to replace the cooling on the magnesium ions by a red sideband. And of course, on top of this, optimize the values of these parameters, Rabi frequencies and polarizations. And then indeed, we find that there are no more transitions out of the target state. And the only remaining source of errors is anomalous heating. Okay, now it depends on the heating rate, how close you come to 100%. So if you have a heating rate of 10 Hertz, it's this. And if it's 1 Hertz, it's even less. And if it's 100 Hertz, you're not improving so much beyond the previous result. Okay, so when I showed these results to Didi, he actually was more excited than I expected by a fact that I had been ignorant of, namely that you don't need the magnesium ions any longer because you replace the sympathetic cooling by another sideband laser. So here's the experimental implementation of the protocol that we suggested with just the two beryllium ions. And we're not yet at 100%, but close to 95. And let's just say we understand where the remaining errors comes from. And what is, I think, from a theoretical point more interesting is to ask, what is the fundamental limit for the errors? Can we get close to the 4 nines? Or how much power does DD need to buy in his next laser in order to reach these 4 nines? And the answer is, again, it depends on your heating rate. Okay, so if your heating rate is 10 hertz, it doesn't help you to buy a lot of laser power because you'll saturate. But if you can push the heating rate close to 0 on the timescale of the experiment, and DD tells me that he thinks he can do that, then this is the power that you need. Okay, so let me finish with an outlook to many-body systems. So here's our trapped ion example for a driven dissipative evolution. And about 15 years ago, there were a lot of theoretical proposals in the literature on preparing many-body states with driven dissipative evolution. And at the time, I was very skeptical because natural dissipation, like spontaneous emission in the case of our ions, may lead to leakage, may not always be available, and typically is local. So how do you get the non-local jump operators that were needed in these proposals? Well, recently, we've seen the emergence of a new field of measurement-induced dynamics. The idea is don't rely on dissipation, which is there naturally, but engineer it via measurements or via coupling to auxiliaries. And here's a proposal from my collaborators of doing this to prepare the AKLT state, a topological state, for a spin-1 chain with periodic boundary conditions. And at each link between two sides, you have to create these 5 jump operators, and then you can drive into this state. Okay, so this, as I said, is a topological state. Let me skip this. The stairman is already standing up. The key point here is that of this proposal is that you need an extensive number of detector qubits, namely 5n detector qubits, if you have a spin chain of n sides. So that, to me, doesn't look so promising. And there is an alternative proposal by those guys using coherent evolution and fusion measurements, but it's also extensive in system size. It turns out you don't need to be extensive in system size. It's actually sufficient to cool just on a single link. And you can still drive in finite time into the ground state, in the AKLT state. And of course, the rate with which you do this goes down as the system size increases, but you go there. So why does this work? Well, what you have to look at is the reduced state on the cooled link. Okay, so you project the target state, the AKLT state, which lives on the whole chain, onto the reduced link. And then you see that all the excited states have non-zero overlap with what we call the hot subspace, the excited state. And therefore, if you manage locally to cool all the states in the local subspace, eventually you will pump all the excited states into the ground state. So here's now the recipe. You partition, based on your target state, you can partition this Hilbert space on the cooled link into a cold subspace and a hot subspace. And then you span the whole hot subspace with jump operators that cool these excitations. And you can formalize this in terms of a necessary condition for dilute cooling. Namely, the target state then reduced to the cooled link needs to be distinguishable from the excited state, from the reduced hot states. Okay, and then the question is, how general is this? Is it limited to AKLT? And our answer is no. And this answer we can again phrase using tools from control theory. Remember the Lie algebra techniques I told you earlier. And that is, we can define a space that we call the kernelizer, which is the space that contains all quasi-local operators that preserve the target state. And now we argue, if you want to generate control such a many-body system, you should be able to construct these quasi-local interactions. So let's allow to draw additional interaction terms from this space. And then, if we have enough of those interactions, we are guaranteed that we will be able to prepare the target state. Okay, so if we have controllability on the kernelizer, we will be able to fulfill a sufficient condition for cooling. And so, first of all, we need that we have respect that our target state is respected. Then we need to check that we have enough interactions that can be engineered in a quasi-local way to propagate the excitations to the cooled link. And then we can construct the jump operators on the cooled link. And this works for any frustration-free quasi-local Hamiltonian. We have a second example in the paper, and we're currently looking in whether this can be generalized further or not. Okay, so with this, Chairman is standing up. Let me summarize my talk. I discussed how we can use controllability analysis to minimize the number of controls in qubit architecture designs, and how we can use optimal control theory to derive protocols for the fastest operation of state preparation and gates. And I showed you how we can use ideas from quantum reservoir engineering to minimize the number of detector qubits that we need for dilute cooling into non-trivial many-body states. Here's the students and former students from my group who have done this work. Fernando on the controllability, Sabrina for the Rydberg state, Daniel for the chaotic fluctuations, Carl for the dissipative ions, and Josias for the many-body part. This is work done in really nice collaborations, both with other theoreticians and with experiments. I'll thank my funding agencies, and I thank you for your attention.
Thank you.